So this is 11.5 margin of error. And there's two vocab words up here. And we're going to talk about margin of error in just a little bit. But I'm going to go ahead and give you a rough idea of what it is. Margin of error is how, is that the best wording? Let's say it's how close a sample's mean or maybe standard deviation is to the true parameter, which is the population. Let me reword that. Is to the true population's mean or, standard deviation. I don't know why I'm mentioning standard deviation, but it's how close a sample's mean is to the true population's mean. Now, when you talk about the population, you're talking about a parameter. Okay, so how close a sample's mean is to the true population's mean. And we do this with the plus or minus symbol. I'm not going to talk a lot about this because it really just bogs this lesson down from what it is. What is a sampling distribution? A sampling distribution is where you take a lot of samples, you take several samples, and you arrange them on a histogram. And what you discover, hopefully, it's not always true, that you get a normal distribution. Who would have thought? Okay, which means you get to use all the rules like the bell curve or the empirical rule, okay? So it turns out that if you take lots and lots of samples, you'll get something that lays out like a perfect bell curve, usually, or it's very close to one. So that's where some of this stuff is coming from. All right, so to find the mean of a population, we sample. Is this sample going to be 100% correct? No. What we do is we create confidence intervals using what's called the margin of error. So we just had an election not too long ago, but a lot of this stuff you'll see in the news talking about voting, okay? So a poll says that 53% of all likely voters will vote for, I'm not going to get political, candidate A with a margin of plus or minus 4%. So what does that mean? That means between 49 and 57% of all likely voters will vote for candidate A. It's not actually guaranteed that candidate A wins because candidate B could get 51% or they could get 43%. So, and when we write these out in an algebra class or a stats class, what we would do is we would write, if I was plugged in, I would be writing, didn't have my little board plugged in, we would write that interval from 49 to 57. So the intervals we write are the margin of error minus, sorry, I don't know why I'm writing margin of error. They are the sample estimate is 53%, which we really shouldn't call X bar. Since it's a poll, it's a sample, it's really just called S. But it's the sample plus or minus the mean, but I'm going to leave it X bar, minus the margin of error, comma, the sample plus the margin of error. So that's where I got these numbers. 53 minus 4 is 49, and 53 plus 4 is 57. That's how we write them out in this class, all right? All right, so here's the concepts for margin of errors. There's going to be some formulas on this page. There's also a definition of margin of error. Margin of error gives the maximum expected difference between the sample result and the population parameter. And you've got some formulas here. You've got one for quantitative data. The margin of error is 2 sigmas divided by the square root of n. Now, the 2 sigmas is coming, your textbook focuses only on 95% confidence. So why is this formula giving a 95% confidence interval? And what do you see that indicates 95% confidence? What you should see, and a lot of you won't write this, but this is very important. You think about your bell curve, and you have the mean in the middle. You have the mean plus a sigma, the mean plus 2 sigmas. You have the mean minus a sigma, and you have the mean minus 2 sigmas. From here to here is 95% of the curve. That's why they're talking about 2 sigma. So the margin of error for quantitative data is 2 standard deviations divided by the square root of n. I really can't give you a very good explanation of why they had divided by square root of n. It has to deal with sampling statistics, and I'm not talking about all that stuff. For categorical data, it's just 1 over the square root of n. And I have never bothered to look up why that is the way it is. It's just what has always been. So we go with it. Moving forward. The College Board recently reported that the mean score on the SAT mathematics exam is 508 with a standard deviation of 121. Washington High believes that its seniors score considerably higher than the national average, so the school randomly sampled scores from 200 seniors, finding a mean score of 550. Is Washington High correct in its belief? So the first thing that we need to do is we need to establish qualitative or quantitative, qualitative being categorical. So that's my first real question, qualitative or quantitative, which is categorical, or quantitative, which is numerical. And this for sure is definitely going to be quantitative. So because it's quantitative, I get to use little formula, right? Your margin of error formula for well, it doesn't say this, but we're going to do 95% confidence interval. And there's a reason we're going to do 95% confidence. The margin of error is going to be 2 sigmas divided by the square root of n. That looks more like a theta, doesn't it? 2 sigmas divided by the square root of n, which I don't even know what that bottom thing is. It's not an n. All right, so 2 sigmas divided by the root of n. Standard deviation is your sigma, so 221s divided by the square root of 200. I'll carry this out 2 decimal places. That's the way you usually see stats people do it, at least in the beginning stat classes. All right, so we have 2 times 121. That's 242. We're going to divide it by the square root of 200. And we get about 17.11. Now, let's construct the interval, all right? So we're going to take our mean, which is 508. Oh, sorry, 550 for our sample. We're going to do x bar plus the margin of error, and we're going to do x bar minus the margin of error. Okay? So we're going to take our 550, we're going to subtract 17.11. We're also going to do 550 plus 17.11. And we're going to get this confidence interval, which is going to be 542.89. That's wrong. 532.89 to 567.11. This is a 95% confidence interval. Now, what does that mean? So, a lot of y'all just don't want to learn concepts. This means that we are 95% certain that this high school, WH, Washington High, true mean lies between 532.89 and 567.11. Now, the national average is 508. Okay, that's a big deal. Since the national average does not lie on WH's 95% confidence interval, WH can say with 95% confidence their students did considerably better. Now, the emphasis here is on the 95% confidence interval, and I think these are in the notes. If not, it's a good time to define it. The definition of an unusual event. An unusual event is an event that has a 5% chance or less, 5% or less chance of happening. So when we're talking about our relationship to the bell curve, and we talk about this 95% confidence interval, there's your middle, your mean, 1, 2, 3, 1, 2, 3. These two events right here account for 95% of the possibilities. This tail and this tail is 2.5% each, okay? So Washington High's kids, if you look at their data and you look at the national average, they were way higher than that left tail. There wasn't a single range they had on there. So it was unusual that Washington High School was doing that well, and they could justify the claim that they were significantly better because what they did is unusual. That's why. We would not expect the national average to be on their particular confidence interval. So that's kind of where that comes from. All right, we got a couple more of these to do. A random sample of 100 Washington High seniors reveals that 40% plan to take the SAT this year. Use the margin of error to predict the actual proportion of seniors planning to take the exam. So my first real question is this qualitative, which is categorical, or quantitative, which is numerical? And the truth is, there's not enough information given for it to be numerical. It's not quantitative, it's qualitative. It is a category. You either take it or you don't, okay? It's category. So for category, if you just go back 2 slides, that's how you do your margin of error. Your margin of error is going to be 1 over the square root of n. So my margin of error here is we have a random sample of 100 kids. It's 1 over the root of 100, which is 1 over 10, which is as a decimal 0.1, which is cool, or let's just use 10%, okay? 10% is my margin of error. So a random sample of 100 Washington High School seniors reveals that 40% plan to take the SAT this year. Use the margin of error to predict the actual portion of seniors planning to take the exam. So my confidence interval would have 40% minus 10%, and it would have 40% plus 10%. So it would be 30% to 40, sorry, not 40, 50%. That's the confidence interval. And again, what does that mean? It means that we are 95% certain, or we can say with 95% confidence, we believe that the true proportion of seniors taking the SAT lies between 30% and 50%. So 95% confidence. All right, we have an error analysis one here. I like it because this one's done by a coach. A sample of 16 students from a teacher's physical education class. Students attempt to do as many sit-ups as possible in 1 minute. The mean was 10 with a standard deviation of 2. This teacher said the margin of error was, I don't know what happened to the number that goes there, but it seems to me like the teacher said the margin of error was 1/4. What is the teacher's error? Well, the teacher didn't do the formula right. The margin of error is supposed to be 2 standard deviations over the square root of n. So we're going to get 2 times 2, because that's the standard deviation, over the square root of 16. We're going to have 4 over 4, which is 1. The margin of error is 1. Okay? What the teacher did, and I know he was a coach, what the coach did was they did 2 times 2 over 16. They forgot the square root. 2 times 2 is 4. That's what that coach did, because you know it's math. So what this means is that 95% of all students did between 9 and 11 push-ups, or sit-ups in this case. They did 9 to 11. All right, there's the true CI. All right. We don't have too much left. A sample of 40 DHS students' GPAs yields a 99.7% confidence interval for the mean of all DHS students to be 2.1 through 3.7. Now, notice I mentioned 99.7. From your empirical rule, this is 3 sigmas. That's for you dum-dums, that's 3 standard deviations. Okay? So determine the sample's mean. The mean is going to be the number in the middle. That guy right in the middle. Like, that's not that hard. You're going to take 2.1, you're going to take 3.7, you're going to add them together, and you're going to divide by 2. And you're going to do some math. 2.1 plus 3.7 is 5.8. 5.8 cut in half is 2.9. Determine the sample standard deviation. That's going to take some steps, okay? So if this is the middle, if the middle is 2.9, the margin of error is going to be 3.7 minus 2.9, which is going to be 0.8. Now, how's that help me do standard deviation? Okay, since this was 3 standard deviations, the margin of error formula, and again, because it's 3 sigmas, would have been 3 sigmas over the square root of n. I have the margin of error. It's going right there. The margin of error is 0.8, and it must equal 3 sigmas divided by the square root of the sample size, which is 40. All right, so hey, some algebra. We're going to multiply both sides by root 40. So I will have a root of 40 times 8/10 is 3 sigmas. And then I just divide out by 3. And that is going to be my standard deviation. And I didn't go ahead and figure out what root 40 was. I didn't care what root 40 was. I don't care what root 40 is until the very end. I don't. You shouldn't either. So there's my root 40 times 8/10. And I had to divide out the 3 to get sigma. And there's my standard deviation. It's about 1.69. Sigma is about 1.69. All right, create a 95% confidence interval for the mean GPA. So now because I've done part 2, I can do part 3. For a 95% confidence interval, the margin of error is 2 sigmas over the root of n. So sigma is 1.69, 2 times 1.69, sitting pretty over root 40. I need to hurry up. I still got stuff to grade. The second video this morning is about 0.53. I want a 95% confidence interval. I'm going to take my mean, which is 2.9. I'm going to take away 0.53. I'm going to follow that by 2.9 plus 0.53. And that's going to give me 2.37 all the way to 3.43. So what's interesting here is, and pay attention to this too, because I'll ask this question later. The higher the confidence interval, the wider the range. Notice that? The higher the confidence interval, the wider the range, which should make sense. If you give a bigger range, you're more confident that the truth is in there somewhere. And the range is shrunk as we went down to a 95%. All right, 68%. If 99.7 was 3 standard deviations over the root of n, and 95 was 2 standard deviations over the root of n, then 68 has to be a singular sigma divided by root n. Okay, so it's 1.69 divided by root 40. Now this is only a 68% confidence interval. So it's going to be a smaller range of values because you're only 68% confident, or it's only 68% of the population. So 0.26 or 0.27. So let's go back up here to my 2.9. 2.9 minus 0.27, really, that's all it was. 0.27 followed by 2.9 plus 0.27. 2.9 minus 0.27 is 2.63. And 2.9 plus 2.7 is 3.17. All right, a student has a GPA of 3.54. Is this considered unusual? So the unusual events are always going to be about the 95% confidence interval. So think about that. Since unusual is 5% or less, we use the 95% CI. Okay? So my 95% CI is this guy right here. And I can see that 3.54 lies to the right of the 95% CI. And I wish I had more room here, but that's this tail over here, which has a 2.5% chance of happening, which is unusual. So it is unusual, yes, since to the right of the CI, it has a less than 2.5% chance, which is definitely unusual. So a 3.54, based on the data that I threw in front of you, is unusual for a DHS student. All right, 2 more. The mean ACT score is a 20.8. Dresden High School thinks their mean ACT score is significantly higher than the U.S. average. This would have been for the seniors that graduated last year, not the current seniors. They're horrible. A sample of 22 students' ACT scores were analyzed, and a sample mean of 26.7 with a standard deviation of 2.9 was obtained. Create a 95% confidence interval for the mean from the sample of 22 DHS students to back up DHS's claims. All right, so 95% confidence, the margin of error is simply 2 sigma over root n. Standard deviation is 2.9, so it's twice 2.9 divided by the square root of the sample size, root 22. Let's see what we get. By the way, this is dividing by the square root of n, so the bigger the sample, the tighter your confidence interval becomes. This is a remarkably low standard deviation for the ACT because the ACT nationally has a standard deviation of 5.4. It's crazy it's that big, but that's how big it is. So it's around 1.24. All right, so let's make our 95% CI. If I take my mean of 26.7 and I subtract that, I'll have 25.46. That seems right. 25.46. And if I add that, I'll have 28.94. Now, the mean ACT score is a 20.8. That is a nationwide, actually, that's actually too high. The true mean for ACT is 19.4. That's what it was in 2024. It was 19.4. But anyways, Dresden thinks their scores are better. Are they justified in that claim? Yes, they are justified. Since DHS, or sorry, since the national average lies to the left of DHS's confidence interval, that shouldn't happen. DHS can support their claim. Because what this means is since the national average lies left of the Dresden High School's confidence interval, the DHS scores were in the top 97.5% of all averages, all samples. So very, very strong claim. And it shouldn't happen. It should be incredibly unusual because the national average here would be an unusual score at Dresden High School. So there you go. Coach K believes that we have an unusually high chronically absentee rate. We do. I don't know if we still do or not. We used to have a really bad one. The chronically absent student misses 10 or more days of school, and the state yells at us for anything over 10%. The state average for being chronically late is 11.2%. Coach K samples 25 students and finds that 19.8% of them are chronically absent with a sample standard deviation of 4.2%. Construct a 95% confidence interval for the mean of DHS. I don't think Coach K is going to be doing confidence intervals, but he could if he wanted to. Coach K knows some math. He took a lot of math. He taught physics. He ain't stupid. All right, so anyways, on to this. I need to know the margin of error, and it is a 95%. Margin of error is going to be simply 2 standard deviations, which is there it is, 4.2%. Yeah, we'll keep the percentages. We're going to divide that by the square root of 25, so that's going to be 8.4 over 5. Let's see what that is. Come on, calculator. There we go. 8.4 over 5. 1.68. It's 1.68%. All right, so I take my 19.8 and I subtract 1.68 and I get 18.12. I take my 19.8 and I add, I get 21.48. Ooh, compare our confidence interval to that state average of 11.2. Does DHS have a significantly higher rate of chronic absenteeism than the rest of the state? Yes. Yes, it does. If we had a typical absenteeism, the state average would lie inside our confidence interval. And it doesn't. So yes, we have a significantly higher rate of chronic absenteeism. All right, the last one here, we have I didn't give you a histogram, I gave you a frequency distribution chart. Student council wishes to estimate the mean height of a DHS student. They take random samples during break and come up with the following frequency tables. The measurements are in inches. Find the mean and standard deviation of your sample. So I'm going to go to stat, I'm going to go to edit, and I'm going to have to use class midpoints here. The average or the middle number on 57 and 59 is 58. The next one's 61. Okay. The next one is, take a guess, 64. Oh. Oh, man. I wish I had caught this. This has to be fixed. It's not. That's supposed to be 65, 66, 69, 70, 72. There's something wrong there. That's not 69. 68. 69, 71, there we go. 72, and that one stops at 74, 6'2". All right, let's save that. I'll just modify that later. Anyways, glad I caught that. 61 followed by 64 because it was supposed to be an add 3. Next one's going to be 67. I'm using what's called class midpoints. Next one's going to be 70. If you'll pay attention to the table, you'll see that we're adding 3 as we go. And the last one's going to be 73. So those are our data values. They're the class midpoints. And then we have the frequency. All right. Stat, calc, one variable statistics. There is a frequency list. That's second 2. Scroll down to calculate. Bam. Now, we have to use X bar as our mean. The mean is 65, okay? X bar is 65. Now, these are samples, okay? Standard deviation of a sample is S of X. Because these are samples, I have to use SX, okay? Right there, 4.12. And SX is about 4.12. It's a big difference. Just trust me on that one. Mean is going to be X bar. That's not going to change, but we have to use sample for that one. Construct a 95% confidence interval that contains the true mean of all DHS students. So again, we know this. How many kids were in this sample? TI-84 says N is 18. So our margin of error is going to be 2 of these 4.12s divided by the root of 18. I'm sure you're tired of watching me do this by now. It's about 1.94. All right, so here's our mean. 65 minus that, 63.06. And 65 plus that is 66.94. Kind of short, isn't it? That, for future reference, that's 5 foot 3 inches. And that's 5 foot almost 7 inches. That's actually probably about right, believe it or not. My guess is the standard deviation's off a little too much. It should probably be higher. But I guarantee you the true average height of all DH students is somewhere in between that range. A random freshman is found to measure 55%. Is this an unusual event? Yes, it is. Yes. Since 55 inches does not lie in the 95% confidence interval, it has less than a 2.5% chance of happening. It is definitely unusual. So there you go. And that's it. It's not a hard lesson. It's not. Were the notes were a little too long? They were. I don't disagree with that at all.